Okay, for some reason, I think I'm pretty sure I fixed it now. That was pretty weird. I think I use OBS Studio, by the way, for anybody who knows, and for whatever reason, it wants to reset completely every time I reopen it, and then sometimes it has all sorts of weird configuration errors. So there's about a 30-second lag between I think me fixing the problem and people knowing that I fixed it. So apologies for that. It's kind of like the old astronomy joke that if the sun disappeared, we wouldn't know for about 5 minutes, since it takes about 5 minutes for the light from the sun to reach the Earth. Anyway, I suppose it's not really a joke because within some degree of, that's actually true. All right, folks, thanks for your patience. I think what I'd like to talk about today, as I alluded to, is El Nino. Let's keep it simple. Not that El Nino and its impacts on California are necessarily straightforward, but at least in terms of the topical diversity of the day, lots of folks have been asking about that. So let's keep it to El Nino. Anything about El Nino is fair game. What it is, how it's changing or not. But I really want to focus on the El Nino event right now. That's already quite strong in the eastern tropical Pacific and is likely to become stronger still before it peaks later this year, probably sometime this winter, and what the effects might be on California. So those are where I want to keep the focus today, but some things that are peripheral to that I think are also fair game. If there's a couple of questions about the weather next week in California, I can address those too, but I'm not really going to talk about it in my monologue right now. A, because they don't look like extremely consequential storms, and B, there's still kind of a lot of uncertainty, so we'll see how that plays out. So El Nino, and what is it? Well, I've talked about this before, but I'm going to offer about a 1-minute summary of what El Nino is and how it affects California weather, potentially. But I won't get too much into the details, and today's focus will be to take questions. So please do start adding questions to the chat. I want today to be a little bit more interactive than the last couple of sessions have been. There's a good number of viewers on already, so I think they'll probably accumulate some more as this goes on. So El Nino is a one half, essentially, of a semi-periodic natural oscillation that occurs in the ocean, the tropical Pacific Ocean to be exact, that couples strongly with the atmosphere. So this is something that is at least to a first order an oceanic oscillation, but it is so strongly coupled with the atmosphere, and atmospheric feedbacks, self-reinforcing cycles are involved, that you can't really have El Nino if you only had an ocean. You need that interaction between the ocean and the atmosphere to occur. El Nino is a temporary warming of the eastern tropical Pacific Ocean relative to the central or the western tropical Pacific Ocean. La Nina would be a temporary cooling of the eastern tropical Pacific Ocean relative to the western tropical Pacific. The background gradient of temperature in the tropical Pacific Ocean is such that the western tropics are much warmer than the eastern tropics. The main reason for this is there is cold water that upwells off the coast of South America near the equator, and that does not happen on the west side of the Pacific Ocean near Indonesia. Why is that? Well, that has to do with atmospheric circulation, where the wind's directions are coming from, and the interaction between the wind stress on the ocean surface and the ocean itself in a vertical three-dimensional system. I'm not going to get into the details there. It's actually fascinating but somewhat complicated, but suffice it to say, for these purposes, El Nino means unusually warm water in the eastern tropics. La Nina means unusually cool water in the eastern tropics. Currently, we have El Nino conditions, strong El Nino conditions at that, and those are continuing to intensify. And in fact, the models, the coupled ocean and atmosphere models suggest that the current El Nino event will further strengthen potentially into a very strong, or a quote-unquote super El Nino event within the next couple of months. So this is likely to become an event that is historically significant. It won't necessarily be the strongest El Nino event on record, but it will likely end up certainly in the top 10 and perhaps in the top 5 on record. Up there, similar to or even equivalent to in the echelons of 82, 83 or 97, 98. or the one that didn't have the effects we thought it might, the 2015-2016. Those are some of the big El Nino events in recent decades that many of us remember. And so, if El Nino is taking place in the tropical Pacific Ocean, how does it affect California weather? Well, there's a couple of different mechanisms, but the most important one is how it affects what are known as Rossby waves. And you can kind of think of Rossby waves as ripples in the pond being the global atmosphere. And that if you throw a pebble in a pond at a particular location, the ripples are going to emanate outward from right where the pebble went into the water. In the Earth's atmosphere, those ripples from the tropics tend to emanate or radiate outward from the longitude in the tropics where there is the greatest level of tropical thunderstorm activity, known as deep convection. The longitude, or the east-west portion of the basin where that occurs, sort of tells us where the source for those waves, for those atmospheric oscillations is going to be in a particular year or season. And El Nino then can significantly influence it by shifting the region of tropical thunderstorms to the east of where it would otherwise be. In the classic sense, El Nino then shifts them into a position that makes it such that the Gulf of Alaska low likes to deepen in winter, and the subtropical portion of the Pacific jet stream to the west of California is a bit stronger and southeastward shifted than usual. So we have more of a persistent Gulf of Alaska low and a jet stream, a subtropical jet, that is both more prominent further south and stronger than it would usually be. And both of those things tend to lead in a tilt in the odds, especially during stronger El Nino events, towards more active winter patterns across the southern tier of the U.S., and that does include, especially, the central and southern parts of California. Sometimes Northern California, sometimes not. And sometimes not even Southern California, because El Nino does not offer a one-to-one correlation with wintertime precipitation. In fact, it's a very tortured and complicated relationship, although there is a more powerful one than just doing a linear correlation between the two might suggest, because it is strongest precisely for the kind of event that we have right now, which is to say a strong east-based El Nino event. East-based being important because it means that the region of unusually elevated tropical thunderstorm activity is shifted even farther to the east than during a more central Pacific El Nino event, or El Nino Modoki. So what we have right now, a strong east-based El Nino event, and we are now in November, so we're getting into the wet season in California, and so there's all sorts of questions about what's going to happen next. I will pause. There's a couple of questions right now, but I would really encourage folks to submit more questions. And what I will do at a couple of different points in this conversation is probably push the commercial break button while I read the comments, and I will come back after. So if you see an ad or something pop up, that's not me going away. You're not going to miss anything. It's just me taking a break to take a sip of water and then read the questions that have actually come in the meantime. So that's how things typically work. That's sort of the classical textbook explanation in a nutshell as to why the main reason why El Nino can affect California winter precipitation. It also makes California winters generally warmer, although really these days the dominant effect is climate change. Most California winters are much warmer than they used to be, and that kind of outweighs the El Nino-La Nina cycle. So really, it's rather easy to make a prediction that most winters will be warmer than the 20th century average in California, because the vast majority of winters are now warmer than the 20th century average simply because of climate change. But the combination of El Nino, which doesn't necessarily mean warm and tropical, but what it does, it actually results in warmer winter temperatures in parts of California, mainly because it tends to increase storm activity, and the coldest days are usually not the stormy days, but it's the dry and clear nights that get really cold in California during winter, and you get fewer of those during a typical classical El Nino year. So it may not feel warm and balmy, but you really shave off a lot of the much colder days. That's sort of how El Nino can bring about a bit of a warming effect in the southwestern U.S. It's not necessarily because there's tons of tropical air over California or anything like that, although that can happen also. This year, Everything is kind of complicated by the fact that we have, as I've mentioned in previous conversations, gigantic blobs of extremely warm or even record warm ocean temperatures outside of the tropics. So, a lot of those canonical or traditional El Nino connections with California climate are linked to or predicated upon the global oceans being roughly near more average temperature conditions. But right now, they are anything but. And the North Pacific is now exceptionally warm. In fact, the water, even now immediately off the California coast, is now also warm. So I've been talking for much of this year about how it's been really warm over the remote parts of the North Pacific, but near the California coast, it was actually kind of chilly. Well, that's now changed. The water is now anywhere from 1 to several degrees above average across, right along most of the California coast. You may actually be noticing this if you live along the ocean. It's been pretty mild lately. Not necessarily hot, but that elevated baseline temperature of a few degrees warmer than usual is largely coming from those warm oceans. So the whole North Pacific is really warm right now, including the Gulf of Alaska, which is a place that usually gets a bit cooler than average during El Nino because of all the increased storm activity mixing up cold water from beneath. So what do the models say about what might occur this winter? Well, many of them, in fact, a majority of the seasonal models, are pointing towards a significant tilt in the odds towards a wetter than average winter in California. And unlike some previous predictions, this might begin as soon as December. There is some indication now that December could be quite a wet month in California, as well as January through March. But there is some dissonance from among these predictions, and most notably, the European seasonal model, the ECMWF, the SEAS 5 model, which nobody actually seems to know the name of. I didn't until this week. I just called it the European seasonal model, but that's apparently what it's called. But regardless of the acronym, it's a very well-performing seasonal model, and its ensemble is quite mixed regarding what might happen in California this winter. It suggests a much weaker tilt in the odds towards wetter than average conditions this year in California compared to almost all the other global models, which is interesting because it is one of the best performing seasonal global models. So that gives a bit of pause because what the pattern that the European ensemble is showing emerging this winter is one where the Gulf of Alaska stays extremely warm straight through winter, and where there's a bit of a ridge in the place on average, where there is an unusually deep low in the Aleutian low zone during a traditional El Nino, and so therefore, in that ensemble average, California has about equal odds of a wet or dry winter this year, which is kind of extraordinary given the magnitude of El Nino and the east basedness of this particular event. So that gives us a little bit of pause, but we have to remember too that no model is perfect. Even the ensemble itself is only moderately predictive of what might happen. There's a lot that it doesn't capture. So what I think it does is it gives us a reminder that seasonal predictions are difficult and that they never give us any guarantees. But I also think that what the broader ensemble is telling us, so if we look across all of the models in the world and their full ensembles, there is a pretty strong tilt in the odds now. So this would be for the North American multi-model ensemble. So this is sort of an ensemble of ensembles. This means that there are both multiple models being used and also multiple members from each model. So there's a lot of different permutations of what could happen this winter from different modeling centers and using different initial conditions, is really what that means in a nutshell. At this point, the preponderance of evidence points towards a wetter than average winter. And interestingly, right now, although the odds and statistical confidence are highest for Central and Southern California, the North American multi-model ensemble also suggests this would extend through Northern California as well, essentially meaning that all of California, in the most recent update of the North American multi-model ensemble, which came out earlier this week, just on the 8th, so just a couple days ago, suggests that all of California has elevated odds of a wetter than usual winter this year. In fact, the most recent update is coming in quite wet, especially for December and February. I wouldn't read too much into the individual months, but generally, seasonally, the odds that the whole season will end up wetter than average are looking pretty reasonable. So that is going to continue to be my prediction, as it has been before, with the caveat that one of the best performing models in there dissents from that prediction. And I'm not quite sure what to make of it, because the pattern that the European model suggests for this winter is pretty weird, honestly, for a strong El Nino event, and yet that is showing up in the ensemble average for that particular modeling center's predictions for this year. The warm Gulf of Alaska with somewhat ridgy conditions. There are still, even in the European models, slightly more members that are wet versus dry. So even there's a very slight tilt in the odds, but it is pretty slight compared to the much stronger tilt in the odds towards wet from most of the other models. So we don't know what's going to happen this winter, but once again, as I've said before, if I had to put money on it, I'd put my money on wet, although I wouldn't put a lot of money on it. And the challenge, I think, is there's several things going on at background that matter too. One is that the whole world is warmer than it has been in human history currently. So there is 7% per degree centigrade, or 3 to 4% per degree Fahrenheit, more water vapor holding capacity in the atmosphere. That means that the storms that are out there are progressively more juiced up than they used to be. And in this particular year, where global average temperatures are hovering around 1.4, 1.5 degrees centigrade, getting close to 3 degrees Fahrenheit now on a global average basis, at least temporarily, that's a pretty significant increment of extra juice in the atmosphere, on the order of 10+% more than there used to be back in the 20th century. So that's not small, and that's not factoring in the changes in large-scale circulation that come with El Nino. That's just a statement about the whole world as it's warmed. In addition, the North Pacific being very warm, that might mess up the atmospheric teleconnections. It might mess up the sequencing of ridges and troughs and the placement of the jet stream, potentially. So that may be what the European model is seeing, throwing a wrench in things. But it also means that there's even more moisture potentially available in the lower atmosphere, if we do get those atmospheric river storms this winter, for them to pick up even more moisture in the unusually warm nearshore atmosphere contributed by these warmer ocean surface temperatures. So there's a lot going on, and there is certainly, I would say, an elevated potential of a wet winter with several episodes of very wet conditions and flooding. I would say that likelihood is probably higher this year than usual. And all of this comes on the heels of a year, last winter, that was quite wet. And so watersheds are already more saturated, reservoir levels are already running higher than they were going into last winter. So the background antecedent conditions are a little more favorable for quicker development of flooding should we get intense storm sequences at some point this winter. So that's the stage. The likelihood that this winter is significantly warmer than the 20th century average in California is pretty much a slam dunk prediction at this point. The precipitation predictions at seasonal scale are always more uncertain than temperatures, but the combination this year of a very high confidence in a warmer than average winter overall, again, not necessarily a balmy winter, but even if you increase that average temperature by a degree or two, it means that snow line creeps a couple thousand feet up the mountains relative to what it used to be, combined with the more modest but notable tilt in the odds towards more precipitation than average, suggests that this winter's most likely combination is warm and wet. The second likeliest combination is probably near average precipitation, but also warm. And in either of those scenarios, the likelihood of flooding, especially downstream of some of the higher elevation watersheds in California, might be elevated. So that's one consideration. I think with that, I want to take a pause on the monologue portion. There's now enough comments here and questions for me to take a look. So I'll run the brief commercial break. Bear with me while I take a sip of water and read the comments. I'll be back with you in just a couple minutes. And for those who are through the commercial break portion, I'm actually pulling up a map right now since that was requested. I should be able to have that up in just a minute once I'm certain that everyone's on the right side of the break. All right, so there is right now. There's a question. I'm actually got a question about Hawaii. I'm going to answer that first since it's a little bit of a tangent, but I think it's important, and there is actually a pretty strong indication here. The question is from, let's see, from Marty. We always hear about El Nino winters in California, but they also affect Hawaii's level of precipitation too. Can you talk about thoughts on whether we would see relief for super dry conditions in the Hawaiian Islands? Unfortunately, no. In fact, there's actually a very strong indication that this winter will be very dry in Hawaii. So the teleconnections with El Nino, particularly a strong east-based event, are much stronger and subject to higher confidence than the California tilt on the odd towards wet. So unfortunately, to the extent that Hawaii, especially the lee side of the islands, as we saw during the unfortunate and disastrous fire catastrophe on Maui earlier this summer, that is unfortunately likely to get worse rather than better this winter with the rise of El Nino and the strengthening of the event through the winter months. So low precipitation and warm temperatures are likely are likely in Hawaii this winter. In fact, I would actually have significantly more confidence in that than in the precipitation outlook for this winter in California, although I do think there's a tilt towards wet in California too. So, a question from Lori: thoughts about preparations for a strong El Nino event in California? Could this become an arc storm event due to warmer ocean temperatures and warmer air temperatures? So, I can talk a little bit, and the arc storm, for those who don't immediately recognize it, it's actually an acronym that refers to severe storm and potential flood scenarios for California. That I've been involved on the research side on the most recent iteration of this, with Arc Storm 2.0. I've talked about it in previous conversations. We had a big paper come out last summer on this, and there's a Weather West blog post if you search for Arcstorm where you can read all about it. I won't go into the details there except to say just be thinking intense multi-week sequences of storms that result in cumulatively greater flooding as the event goes on. That's kind of what we're talking about in that context. One of the things that we found in that paper last year that we wrote up for Science Advances in the process of doing this ArcStorm 2.0 modeling is that the almost all in the large climate model ensemble world, at least almost all, so 7 out of 8 of the largest projected ArcStorm-like events, both in a cooler historical climate and in a warmer future climate. The ones in the future are bigger and wetter than the historical ones, but this is true of 7 out of 8 of all of them cumulatively, occurred during moderate to strong El Nino events. So there was a clear tilt in the odds towards such multi-week extreme storm sequences happening during strong to very strong El Nino events, which is one reason that gives me pause when we look like we're headed into one of those years. This is one of those years that looks an awful lot like the maps in those ArcStorm predicted events in the climate model ensemble looked like. But here's the thing though, there were also a lot of years that looked like that did not produce ArcStorm level events. So you kind of have to think about the conditional probability. If given a strong El Nino event, is there a higher than usual likelihood of an ArcStorm like flood event in California? At this point, I'm inclined to say yes, there probably is. Does it mean that it's the only type of year in which we could see one? No, absolutely not. And this past winter was a nice counterexample to that, although that was, of course, not quite on the level of the kind of floods that we're talking about in this context. But it does tell us that there probably should be elevated concern regarding those kinds of events precisely in years like this one. And the seasonal predictions right now somewhat reflect this, with a pretty significant tilt in the odds in the North American multi-model ensemble towards wetter than average conditions at seasonal scale. That doesn't tell us about the individual risk of storms. If they come nicely spaced out perfectly evenly and with relatively moderate intensity, then we might not see any significant flooding at all, even if that precipitation prediction came to fruition. But if we do see those storms come with significant intensity, then the fact that the oceans are much warmer than they would usually be, not just due to El Nino, but also due to climate change, the atmosphere is warmer than it used to be, I would say yes. I mean, on average, the water that winter storms are, the intensity essentially, from a precipitation and moisture perspective of winter storms this year is likely to be around 10% greater than it used to be. Doesn't sound like a lot until you realize that, if you're talking about, runoff volume, in a river channel or volume into a reservoir or something, for every 10 inches of rain, that's around an extra inch of rain. An extra inch of rain is not small. And when you're talking about very, very wet places in California, places that during a very wet month can see 20 or even 30 inches of rain, that's several extra inches of rain relative to an equivalent storm from the 20th century. And that's really not negligible. And that's just the average. Some events are probably affected, but to a much larger degree, and some events probably to a lesser degree. But that's a pretty good estimate of what the average effect is going to be during a particular very wet storm or very wet month. And so, yes, El Nino may boost that further because El Nino goes further and says it takes that extra 10% sponginess, water vapor holding capacity of the atmosphere, and it can sometimes juice it up with a stronger jet stream. So you both have more moisture and stronger dynamics potentially. But the big wild card this winter is not so much the moisture, it's more the dynamics. Do these weird blobs of warm water offset the increased atmospheric moisture? Because, of course, you could have a very moist atmosphere and have no precipitation at all. Think of the Persian Gulf coast. Dubai or something. That's actually a very, very oppressively, dangerously humid and hot place, and yet it rarely ever rains there. So moisture in the atmosphere is not enough to produce rain. You need precipitation generating mechanisms. You need storms. You need essentially upward vertical motion in the atmosphere coupled with that moisture to produce the precipitation. So the real wild card is not the moisture, which is definitely increasing and much higher than the background this year. It's a question of squeezing that moisture out in the form of precipitation in storm events. So hopefully that gets to that at least a little bit. Let's see here. All right, so again, I'll continue to encourage folks to submit questions. Could be about El Nino in general, could be about El Nino in a warming climate, could be about this particular El Nino or this particular winter. This is your opportunity since there aren't that many questions today. There's actually a relatively low question to viewer ratio. There's actually a lot of people online I see, but not as many people asking questions. So this is your opportunity. I'm going to go back a little bit. There was one question that I had skipped that I can go back to a little bit. Kevin asks, could you explain how the European versus the American forecast or the forecast models could be so different? In this case, the example is the storms in California incoming for next week. So just for context there, one thing is that often they're not as different as they might appear at face value, which is to say that, and this goes back to some earlier conversations about why is your weather app so bad, despite the fact that weather predictions have gotten steadily better over the past 30 years. And the answer is that they're not using the full suite of information. In this case, your weather app might be taking one individual member from one model and comparing it to one individual member from another model, instead of comparing the full statistical distribution, the full plume of forecast predictions from all of the individual ensemble members from each individual model to one another. They're kind of just taking a random iteration of each model and intercomparing them. And in that context, it's not that surprising that they're kind of randomly going to be different. Often, though, the average of those ensemble distributions is much closer to one another than the individual operational runs that you might see on your weather app. So one is sometimes they're not as different as they appear. Sometimes they are, though. Sometimes they genuinely are different, even if you look at the full ensemble and the averages. And if, when that happens, there can be many reasons, but one is that the whole purpose of having different predictive models, whether they're weather models or climate models, is the idea that, no models are perfect. And we don't know exactly what it would take to build a perfect model, or we would have done so. And so sometimes using different models that make often fairly modestly different assumptions about the way the world works can result in fairly consequential differences in predictions in a complex coupled nonlinear dynamical system, such as the Earth's atmosphere coupled with its oceans. So, in other words, since we don't know what a perfect model is, we have several reasonable estimates as to what the best model might look like, and we don't know which of them is closer to being true, we should probably look at all of them. So one advantage of having different models in the first place is to unsample that uncertainty about what the best model is and how exactly the way the world works is. And so one reason why they're sometimes different is the models themselves are somewhat different. Usually not profoundly so. Energy is still conserved. Force still equals mass times acceleration. But how you parameterize clouds, for example, how precipitation is represented, how initial conditions are ingested. This is one significant difference between the European and the American model. That can result in consequential differences in outcomes, and sometimes those differences are overblown, but sometimes they're quite real, and sometimes they're even desirable, because we don't really know which of them is necessarily more accurate. And so often, when we blend them together, we kind of get a consensus view. It doesn't always mean it's the best of both worlds, but the goal is that blending them together does give you a better estimate of the most likely outcome. So when it comes to this coming winter, even though individually the European model might be the best individually performing model, there's actually quite a bit of evidence, there's research on this, suggesting that even then, there is no single seasonal climate predictive model that performs better than an average of all of the ensembles together. So in other words, there is something emergent about the errors that exist across these different modeling systems that is somewhat compensated for if you mash them all together in an average. And so the statistical average is almost always ends up being a better predictor of the real world than looking at any individual model separately. So that's why I say, even though one of the better models is not suggesting a particular tilt in the odds towards a wet winter in California, it's possible it's onto something, but it's also possible that it is just randomly not correct in this instance. And so my money is still going to be closer to the multi-model ensemble, which does suggest, because most models do suggest a tilt in the odds towards a wetter winter in California. So that will continue to be my prediction unless something changes. And, like any good scientist, I will change my tune if there's strong enough evidence that that's not going to happen. But right now, that's what I'm thinking, and that's partly why. So hopefully that answers that question somewhat at the weather-climate interface. All right, got a few new questions coming in now. Another question from Mark, is the probability of an arc storm-like situation strongly affected by the strength of El Nino? Yes. Weak El Ninos aren't very predictive of anything, actually, in terms of California climate. So this is one reason, by the way, why folks might tell you that there's no relationship between El Nino and California winter precipitation. It's because they've taken a linear correlation between ENSO, or El Nino, and precipitation, or runoff, or something like that. And in fact, the relationship overall is somewhat weak, but it strengthens rather dramatically for both statistically and physically consistent reasons for moderate to strong events. And so once we're in strong to very strong El Nino territory, as we are currently, that relationship does strengthen. So I would say yes. I would, according to what our own research directly suggests that again, 7 out of 8 of our simulated California megaflood events in the model world came during moderate to strong El Nino years. Only one of them was not a moderate to strong El Nino year. I think it was an ENSO neutral year, if I recall. Don't quote me on that. I'd have to look at the data. But again, 7 out of 8 of them were moderate to strong. So there is something about the strength of El Nino that is somewhat nonlinear. And once we get into stronger El Nino territory, it means a lot more. Uh, in a weak El Nino event, I wouldn't necessarily predict a weak tilt in the odds towards wet conditions. I would pretty much say there is no predictive signal from ENSO this year. I just don't think there's much of a signal for weak El Nino events at all. But almost all of the signal that is there comes from the strong events. And so once we get into that territory, a linear correlation, I think, is the wrong way to think about it. It's a nonlinear coupled ocean-atmosphere process. I mean, El Nino itself is literally a nonlinear coupled process, so we probably shouldn't be using linear correlations to talk about its teleconnections, because often that's just not how it works. Even then, there's still no guarantees. There's still a lot of other things going on. One of the reasons why we focus so much on El Nino and La Nina, by the way, in seasonal predictions is not because it's the only thing that matters, but it's because it's one of the only things that that seasonal models seem to be able to get right. So there's a lot of other things that occur that, maybe it's just random noise and that's why they don't get them right, but also there's probably some other important processes that just aren't very well represented. So El Nino is clearly very important, but one of the other reasons why we keep harping on it for seasonal predictions, despite the fact it doesn't give you an extremely confident forecast, is it's one of the only things we have to go on. Seasonal predictions are still, to be quite honest, not very good. And we haven't made a lot of progress, actually. This is one area where initial conditioned multi-month outlooks are just not great when it comes to precipitation. They can get pretty good now when it comes to temperature, which is why I'm pretty confident this winter will be warmer than average across California and really most of the western US. But precipitation remains stubbornly difficult to get right at seasonal scale for a variety of reasons. And El Nino is one of the only things, and in particular, strong El Nino events, or strong La Nina events at the opposite end of the spectrum, are one of the few things that actually do still seem to be meaningful, and that the models can do a pretty good job at predicting. But the problem is, because they don't capture everything else that might interfere with those signals, that's why seasonal predictions essentially aren't better. So we talk about it because we know it's important and we understand it pretty well. It doesn't mean that other things aren't important, it just means that we don't understand them as well, and or we can't rely on the models we have available to us at this time to do a better job. Could machine learning and artificial intelligence based seasonal predictive models do a better job? That is a great question, and I know some folks are working on it, and I think at some point I probably have a conversation actually with some other folks about AI and machine learning and weather and climate science. I think that's a topic of growing interest. I know there's a lot of folks in California in particular who are really interested in that interface. So stay tuned. It might do when the weather is quieter during a lull at some point. That might be a good time to have that conversation about these new kinds of predictive models that are not just directly essentially encoding the laws of physics and chemistry as we know them, because there is this whole other realm of modeling that is rapidly coming online. In fact, some folks would argue that there's a revolution in weather science right now. Interestingly, it has not yet extended to climate science because it appears it to be a much harder problem. The AI models are not getting climate projections right nearly as easily as they're getting short-term weather predictions right, which is perhaps not that surprising for those of us who study these things, is in terms of the type of prediction you're trying to make. As we've talked about before, one is deterministic, the weather forecast, predicting the specific weather at a particular place and time, not so far in the future, versus probabilistic, predicting the full envelope of possible weather conditions over broader regions over a more distant period of time. So they are different prediction problems. It's not that surprising that a model you built to address one might not be ideally suited to addressing the other. But that's a topic for another day, and it's a bit of a tangent for now, so I want to go back to answering some more questions. So the mic has not cut out, but I'm just taking a moment to take another sip of water and read as they've come in. All right, Josh asks, if we do have a wet winter in California this year, what effects would the existing Lake Tulare potentially have on flood control in the Central Valley? Well, This is an interesting operational question for the flood management folks, but I'll opine a little bit. Uh, there's not that much water left in Tulare Lake, but it will. What is there now is likely to remain through next spring at least, and will probably, in all likelihood, that is going to re-expand this winter. So there will be re-flooding of some areas that previously flooded, dried out over the summer and fall, and will probably become inundated again next year. How much that occurs is going to be a kind of an open question. But it will depend both on snow levels, so how warm this winter will be. And again, as I mentioned, it looks quite likely to be a warm winter overall. It's also going to depend on how much actual precipitation falls. And as I mentioned before, there is at least a modest tilt in the odds towards above average precipitation. And Tulare Lake, that basin, of course, drains the southern Sierra, and that is probably within the part of California that is most likely to see wetter than average conditions this year. So I think the level of re-inundation or even expanded inundation beyond what happened last year will depend on the sequencing of storms. Do they come in quick succession? Are they particularly intense? Are they particularly warm? I think if we can check at least one of those boxes, and especially if we check two of those boxes in the same sequence, the answer is it will probably flood extensively again. But that is conditional on checking, I think, two of those boxes. And I do think there's an elevated likelihood of checking those boxes this winter, but again, that's a probabilistic rather than a deterministic statement about that particular risk. I think the other piece of this is, will it affect flood control elsewhere? And I think the reality is Tulare Lake, unless it reached an extremely high level, does not really have an outlet. It's a basin in the southern San Joaquin Valley. So I don't think Tulare Lake itself filling has direct, to my knowledge, flood control implications for outside of the potential lake inundation zone itself. I could potentially be wrong regarding smaller watersheds within the basin, but generally speaking, I don't think it's a primary constraint on upstream flood control. But could the fact that it's full, could it affect the communities within the basin that flooded last year, or places that narrowly avoided flooding last year that would be at risk this year? Yes, that's absolutely a possibility. It's probably more likely this year than it would usually be for a variety of reasons now, partly just because there's already some water there. So there's less dry soil to take up that volume of water that might enter. The other question is, from a broader perspective, do other lakes filling, I guess, the ones that are maybe up in the Sierra Western Slope that have reservoirs on them in many cases, do those being higher than they were in the past, or that they might fill up quickly affect flood control? And the answer to that is more clearly yes. This is something that dam operators and flood managers prepare for. This is definitely part of the operational and contingency planning process. But yes, generally speaking, the more water you have in a reservoir, so in a lake that's upstream of a dam, the less headroom you have to maneuver for flood risk. So this is something that, that's always, that's ever a consideration when operating this infrastructure. But that is the nature of things in this part of the world, where there's always this tension between drought and flood, and you don't want to release too much water if you're not certain it's going to be a wet winter, but you also don't want to be caught flat-footed if it turns out that you're rapidly filling your reservoirs and you need that control space for flood management and dam safety reasons. So, this is not news to folks who operate water infrastructure, but it is a real consideration. And it is one reason why I think the flood risk this winter is higher. It's not just because, perhaps not even primarily, because there's a tilt in the odds towards modestly wetter conditions than average this winter, but I would actually say that the other two pieces are maybe more influential in that statement, which is to say the antecedents are wetter, soils are not as dry as they usually would be going into winter, reservoir levels are higher, there's already water in Tulare Lake Basin, and there's fairly high confidence that this winter will be warmer than the 20th century average. So those three things put together give us a bit of a sense of what might be coming. So there's a question from Jeremy. Well, how will the upcoming El Nino just to be totally clear, we're already in it. It's already moderate to strong, but it's likely to get stronger. What influence will that have on mean or average sea levels on the coast, presumably of California? This is a good question. During El Nino, generally, particularly during a strong event, there is literally an eastward slosh of ocean water in the tropical Pacific Ocean. So in the tropics, there is, on average, a tilt, literally a tilt in the sea slope. I don't remember exactly how much it is, but I believe it's a couple of feet, or several feet, from the West Pacific all the way to the East Pacific. Of course, it's imperceptible. It's not like you're riding a wave if you were on a sailboat along the equator, because it's several feet over the course of thousands of miles, so it's an imperceptibly gradual slope. But the sea surface itself is actually sloped like this because of atmospheric and ocean circulation dynamics. Some of that tilt actually sloshes eastward, so it becomes slightly more level during a strong El Nino event. So there can be some elevation of sea level in the tropics off the west coast of South America, partly for that reason. And there can also be something that's called a coastally trapped Kelvin wave. So an oceanic Kelvin wave that propagates poleward, in the case of the northern hemisphere, northward along the west coast. This isn't like a gigantic cresting ocean wave or anything, or it's not like a tsunami. It's pretty imperceptible at the surface. But what it can do during stronger El Nino events is you can tend to see some of those coastally trapped Kelvin waves elevate coastal sea level. Now, that's going out a little bit on a limb. I've heard some mixed opinions from oceanographers on this front, but it does seem like, at least during some significant El Nino events, we do tend to see these coastally propagating, coastally trapped Kelvin waves move poleward along the coast in ways that can raise sea level. And we have seen this, I believe, in 82, 83 in California, and 97, 98. There were significantly elevated sea levels in California, and including in the San Francisco Bay. So I'll take another closer look at that, see if there's any new evidence. That's a good question that I don't have a complete answer to at the moment, but it would be good to see if there's been any updated research on that recently. I'm not totally sure. Let's see. Okay, here's a good one from Jack Lee. Does El Nino and warmer conditions in general correlate with less snowfall in the Sierra? So the interesting thing is, with stronger El Nino events, there is a bifurcated response that is a function of elevation. What that actually means is that at very high elevations, you tend to see significantly more snow during El Nino years, but at more moderate elevations, you tend to see less snow. And this makes sense if you think about it primarily from a precipitation perspective. If in the southern and central Sierra in particular, there's a tilt in the odds towards higher precipitation during strong El Nino events, but also a tilt in the odds towards warmer than average conditions, then you're going to see more liquid equivalent, but you're going to see higher freezing lines. So if you're at 3, 4, 5, or even 6,000 feet, your odds of heavy accumulating snowfall goes down. But if you're at 7, 8, 9,000 feet in the mountains at the higher elevations, your odds of heavy accumulating snowfall goes up, because if your temperatures rise by a couple of degrees and you're right at the freezing line to begin with, so say you're at 32 Fahrenheit and it gets 2 degrees warmer, you're going to get a nice cold rain instead of snow. But if you're already at 28 degrees at the top of a mountain somewhere, at the peak above South Lake Tahoe or something like that at one of the ski resorts, if you're at 28 degrees and you warm 2 degrees, well, congratulations, you're still below freezing, and you got a whole lot more water falling from the sky, and so therefore you got a whole lot more snow. So there is elevational dependence of the effect. So there's both latitudinal and elevational. In the northern Sierra, this relationship is quite weak. That's partly because the northern Sierra is not as high as the central and southern Sierra. The mountains are physically higher there, and the teleconnections with El Nino are stronger the further south you go. So this, what I'm saying, is mainly true of the central and southern Sierra. So I would expect to see, if the seasonal outlook is right, that tilt in the odds would be towards well above average snowfall at very high elevations. We're talking, like, again, above 6,000 feet, maybe even above 7,000 feet. and probably below average snowfall at lower elevations. So really, especially below 5,000 feet, but perhaps below 6,000 feet. So somewhere in there will be a dividing line between places that are likely to see more snowfall versus less. And this is this complex interplay between temperatures on the one hand, precipitation, volume on the other, and also elevation. And as I mentioned, in a warming climate, we're seeing snow lines creeping up the mountains in general. Last year was an enormous outlier. Last winter was very cold in California, and there was a tremendous amount of lower elevation snow. Frankly, I was very surprised to see that. It's an indication that the natural variability is alive and well still, even in a warming climate. But I don't think we're going to see another winter like that, frankly, in a very long time, perhaps ever, honestly, as the climate continues to warm. So last winter was not necessarily representative of the future from a temperature and snow perspective, but very much contrary to the long-term trend. Now, will we see more winters like last winter with very wet conditions? That's a different story, and there I think the answer is yes, as well as more very dry winters. This is a signature of increasing precipitation whiplash. But that snow effect is interesting, and in a warming climate, there are interesting indications that as mean snowfall declines in most places, California included, extreme snowfalls might not decline or might even increase in sufficiently high elevation cold places. So if you're at the top of a mountain or the crest of the Sierra Nevada up at 8, 9, 10,000 feet, granted, very few people live up there and there's not a whole lot of land at that elevation, but it does exist. You might see bigger snowstorms in a warming climate because you just get more and more moisture and you're still on the correct side of the freezing line. But at lower elevations, even if you do see bigger winter storms, those rising temperatures pretty much outweigh that fact, and you end up getting more rain rather than snow. So I have a few more minutes, and it looks like there's a few more questions, so that might work well. Okay, a question from John. Do we have a good explanation for why Northern California was significantly cooler this year compared to the last few? Not really. And one thing to realize is that the last winter was exceptionally cold. Like, it was the coldest winter in several decades. That was genuinely notable. And then the spring was pretty cold as well. The summer was less cold. It was much milder, and actually this autumn has, on average, in most parts of California, once again, we're back to warmer than average. But for the annual value this year, as is noted, will be way lower than the last several years. Of course, that's a pretty skewed sample because most of the last 10 years have been the warmest years on record in California. And so actually, if you take this year and look at it back in a historical context, it's not a remarkable year. In fact, even this past winter, despite being the coldest in decades, would have been a fairly ordinary winter temperature-wise 70 or 80 years ago in California. So, this is partly shifting baseline syndrome, but it's also, there is something weird that happened this past year. Last winter was decidedly crazy. Not just because of the onslaught of storms, but because a lot of them were very cold storms. I mean, there were disruptive snowfalls. There were people trapped in the mountains for weeks. That's a big deal, and that was really not foreseen at all in the seasonal prediction. So, honestly, at the pace of science, it's too early to have answers to that. We may never have answers as to specifically what caused that, but even if people are going to attempt those studies, they just aren't out yet. I'll be at the AGU conference this year in December in San Francisco, so maybe I'll keep an eye out for abstracts related to that. We'll see if there's anybody's working on that question right now. But as of right now, I don't have really a very satisfying answer as to what went on this past winter, except to say that almost everything about global climate in 2023 has been utterly off the rails. Everything has been wild. And ironically, California, despite what happened last winter, and last winter being crazy, saw a very mild spring, summer, and autumn compared to the onslaught of just record-shattering extremes of all types that are happening elsewhere in the world right now, mainly with extreme heat and extreme precipitation, or extreme wildfires. California didn't see any of those this summer, I guess with the exception, though, of Tropical Storm Hillary, which was not a devastating event, but was certainly a highly anomalous one that did cause damage and disruption in Southern California. So it's been a weird year. Let's just put it that way. And that might not be ending anytime soon. 2024 could well be weirder based on what we're seeing right now. So buckle up. All right, and since this is the last question I'll answer for today, but it is germane to next week. The question is from Alec about what are my thoughts on the potential for rain and snow next week in California. And as I've discussed on the blog, on the Weather West blog, and in the comments section, you should check that out since I often have additional thoughts there that go beyond what the blog posts say. The ensembles are still suggesting that a return to pretty wet weather in California next week, potentially wetter than usual for mid-November still. They've backed off a little bit on average with the intensity of the storms, and they've been delayed by a few days. So it's less likely that there'll be a particularly strong windstorm associated with this event, but there could still be some good rains. In fact, there could be unusually heavy November rain and possibly snow, although there's a lot of uncertainty. The jet stream is doing some pretty wild, wiggly things over the northeastern Pacific Ocean, and it's not totally clear where the pattern is going to set up, and whether the jet stream will be in a favorable position, to strengthen storms or weaken them as they come ashore next week. So whether the storms will be weakening or strengthening as they come ashore, I don't know yet. It's still a little bit too far out. There's still some uncertainty, but overall, there's still pretty high confidence in a shift towards wetter, more active conditions next week in California than the state has been experiencing. So it's just a question of timing and magnitude. But that shift in the pattern is still there. It still looks pretty wet next week. Maybe not quite as wet as initially anticipated, but it should still be pretty significant water potential for mid-November. And in central and northern California, we'll likely shut down whatever vestiges of fire season remain, not that it was very active. In Southern California, where things have been a bit more active, this might also help if the storms can make it that far south, which it looks like they might, bringing a widespread soaking rain to Southern California. So I still think this could be a statewide significant precipitation event, but probably not a big deal, major disruptive or damaging storm event. Just a good old November rain that will come reasonably well timed to sort of shut down fire season in places where it isn't already shut down, especially in the south. All right, so I think with that, I'm going to wrap up this session. I will be traveling next week. So I may not get a chance to do one then. Perhaps there'll be a pop-up one on short notice, or I may try and do one next Friday, so a week from today. So stay tuned. If there isn't anything next week, I assure you there'll be one the following week. So thanks again, everybody, and I will see you next time.